So last class we introduced this idea of the enthalpy change. Enthalpy can be thought of as that portion of the internal energy of the system that's not related to work. We also introduced this internal energy of the system would be equal to Q minus P delta V, where P delta V would represent the work, and under constant pressure, this enthalpy is equal to QP. Now, we can rewrite this such that it's equal plus P delta V, a little bit of rearrangement, and we can say that the delta H of this would be equal to delta E plus P delta V. And so, long story short, we can think of the heat output at constant pressure within a system represents the enthalpy change of that reaction. And that's usually per mole. So another way of thinking about it is that for a given reaction, H2O liquid going to H2O as a solid, the enthalpy change of that reaction, delta H, usually written as Rxn, is equal to 6.01 kilojoules, or kilojoules per mole. What that represents is that for 1 mole of this reaction, 1 mole of this reactant, it requires the release of 6.01 kilojoules of material. All right, so last week we talked about how to capture those, how to measure those using calorimetry. Okay, we can use calorimetry to obtain Qs at constant, because we can use the Q of the surroundings is equal to negative Q of the system, and we can set it up so that we are measuring the enthalpy change, or the heat output of those systems. So quick and dirty, enthalpy is the amount of heat that the system releases. It's inherent heat energy. Another way of thinking about it is we can think of it as a component of the reaction. One way of believing this is, well, you know, H2O liquid going to H2O solid plus 601 kilojoules. We could think of it as a output of that system. Now, the reason it's negative is because it's being released by the system, but here we just write it as a positive value. So, the freezing of ice releases 6 kilojoules of energy for 1 mole of ice. Well, let's put this into practice. How much heat is needed to melt 1 kilogram of ice at 0 degrees centigrade? How much energy? Well, the enthalpy change is related to how much heat is required. And so, given that reaction, we know that there's an enthalpy change associated. So how much heat is needed to melt 1 kilogram of ice? Well, a kilogram is worthless to us. 1 kilogram of water is, we know, from 1 kilogram of H2O, that is equivalent to 1,000 grams of H2O. And for every 18 grams of H2O, that is equivalent to 1 mole of H2O. Says that there are 55.5 moles of water present. And so, 1 kilogram of ice, about 2 pounds, is 55 moles of water. these quantities are stoichiometric. We know for so many moles of water, it releases so many joules. So, in this case, from the stoichiometry, 1 mole of water is equivalent to negative 6.01 kilojoules, requiring 338 kilojoules of energy. Now, this would be a negative 338 kilojoules. But that's not right. All right? A negative 338 kilojoules, that says that that much heat is released. Well, we were melting ice. Heat doesn't flow out of melting ice. Heat flows into melting ice. So we have to take into account that when we actually melt ice, this reaction is flipped. H2O solid going to H2O liquid. And that, when we flip a reaction, changes the sign. The delta H of that reaction would be equal to 6,001 kilojoules per mole. This is a stoichiometric quantity. You double the stoichiometry of the reaction, you double the heat change. You double the heat released or absorbed. So in reality, it would take 333 kilojoules of heat to absorbed. And this is where common sense comes in. Sometimes it's better just to neglect the sign and deal with the amount of heat flowing into or out of the reaction. That's one of the advantages of this sort of idea of writing it. You can write the heat as a starting material or as a product and think of it. Particularly when we get to equilibrium, we can see that the heat as a starting material or product will actually affect the equilibrium direction. But that's next semester. And use your common sense. Heat flowing out of the system or heat flowing into the system represents sign. Again, heat flowing out is an exothermic reaction. Heat flowing in is an endothermic reaction. So let's take a look at another reaction. And in this case, we have another exothermic reaction. We can tell this is an exothermic reaction because it has a negative enthalpy change. So, the question is basically, given 87.9 grams of SO2, how much heat is absorbed or lost, assuming complete reaction? Very typical problem. In fact, anything you do normally with stoichiometry, you can do with the heat as well. This is why we spent the past 6-7 weeks dealing with counting moles, because once we know how many moles, we can actually relate it to other quantities. So, given 87.9 grams of SO2, we can figure out how much heat is absorbed or lost, assuming complete reaction. Well, we know that this is going to be heat released. And again, the reason for that is the sign on the enthalpy. Everything after that is just gravy. When you see a reaction written and an enthalpy change associated with that reaction, the assumption is for the whole reaction. So again, this would represent a release of 198.2 kilojoules, assuming 2 moles of SO2 and 1 mole of O2. That assumes you have enough material. So they have excess O2, and so we have to put this into effect. From the molecular weight of SO2, we can figure out the number of moles of SO2 used. But here's, again, it's a stoichiometric quantity. So we know that for every 2 moles of SO2, that releases 198 kilojoules of energy, allowing us to calculate our answer. 135 kilojoules. And for the sake of completeness, we'd say this is negative 135 kilojoules or 135 kilojoules released. You can't have a negative amount released. That's like, so I'm not going to deal with semantics, though. We're not saying, all right, an answer of negative 135 is fine, or 135 kilojoules released. If you just wrote 135, though, that would be wrong, because it's not a positive 135. Enthalpy is a stoichiometric quantity, and so we can use this to predict how much heat or is absorbed or lost during a reaction. So let's talk about enthalpy change in general. So up to this point, we've been dealing with the enthalpy change of a reaction. So it's the enthalpy change of the reaction. Now, as this implies, anything delta would represent the H of the final minus the H of the initial. And so the enthalpy of each component, in this case the reaction, is an inherent part of the chemistry, an inherent part of the compounds. But how do we measure it? So the problem is elevation, for instance. When you have elevation, where you are, your elevation by itself is not a very big deal. There's these awesome mountains in Wyoming called the Snowy Range. They're beautiful. The highest peak in the Snowy Range is 12,000 feet. And so you can hike up this 12,000 foot peak in half a day, up and down half a day. Perfect lunch hike. All right. So the thing is, it's like, how are you able to do this at 12,000 feet? That's the height of the mountain, 12,000 feet. But the thing is, you start at about 10,000 to begin with. All right. So while you can say you've hiked up to a 12,000 foot peak, you've really only climbed 2,000 feet. So while elevation can be thought of as relative to where you start, the change in the elevation is still going to be the same. And so, like elevation, materials enthalpy is on a relative scale. And so we'd care less about the internal enthalpy than the enthalpy relative to some baseline, the sea level, so to speak. So we define the sea level. So what we do is we compare the enthalpy of compounds against the enthalpy of their elements. And so for this, we can define a new quantity, the enthalpy of formation, delta H formation. Now, you may often see it written as with a little degree sign. This is enthalpy of formation measured under standard state conditions. Now, standard state conditions in thermodynamics is usually a little bit different than standard state conditions with gases. It's usually 25 degrees centigrade rather than 0 degrees centigrade, but it's usually 1 atmosphere. The actual difference between the one we see in gas laws and the one we see in thermodynamics is actually very small. It's almost negligible in many of the calculations we're doing. Usually also we're dealing with a concentration of 1 molar as well. So standard state, enthalpy of formation at standard state represents a sort of baseline which we compare materials to. And so we can think of this, so we can think about the enthalpy change of a reaction as being related to the sum of the delta H of formation of the products minus the sum of the delta H formation of the reactants. Now, how do we calculate these delta H's of formation? It turns out that the delta H of formation is the enthalpy change of the formation reaction. Delta H formation is equal to, so what is this formation reaction? Delta H of formation is the enthalpy of formation. Well, it's the enthalpy change associated with the formation reaction. So what is this formation? Just as a little clue, these little subscripts, F, A, RXN, sub, represent certain specific reactions. Combustion, delta H of combustion, the enthalpy change of a combustion reaction. So your job is to know what reaction is associated with each of these little symbols. So what is the formation reaction? The formation reaction is the reaction of a compound's constituent elements to create 1 mole of that compound. So, for instance, the delta H of formation of carbon monoxide would represent carbon in its most stable state as a solid plus 1/2 O2 going to CO gas. Delta H formation of something like H2SO4 would represent 1 mole of H2 gas plus sulfur plus 2 O2s. This is solid sulfur. This would be gaseous oxygen going to 1 mole of H2SO4 liquid. The enthalpy change associated with this reaction would be the enthalpy of formation. If you measured these reactions under standard state conditions, this would represent the standard enthalpy of formation. So it's the formation reaction. Take the elements, combine them in the appropriate stoichiometry to produce the compound. Unfortunately, these are bull. I mean, these aren't real reactions. This doesn't really happen. The reason we do this is because we define the enthalpy of formation of an element is equal to being equal to 0. And so when you do the delta H of these reactions, where you have products minus of the products minus the delta H formation of the reactants, this value drops out. And so you're just left with the enthalpy of formation of the products as a viable option. Now, sometimes you can take things like carbon plus O2 going to CO2 gas, and the delta H of that reaction can be measured. And so if you take 1 mole of carbon and 1 mole of O2 and you heat them up in a container and you allow them to react completely, this is called fire, you can obtain carbon dioxide, and from that reaction, if you did it in a bomb calorimeter, enthalpy change of the reaction would turn out to be negative 393 kilojoules. And you could then know that that would be the delta H of formation for CO2. Now, if you tried to do the same reaction up here with carbon monoxide, you'd find that it'd be impossible to get at because some of the carbon would react with with oxygen to produce carbon dioxide. You'd have limiting reagent problems, and so you would get a mess. Your heat obtained wouldn't be effective for measuring the carbon monoxide.